All right, today we have a cozy classroom. Lecture 18, as promised, we're going to be talking about the latest in machine learning on graphs. I'll try to go as much as my voice allows me because I got a bad cold in the past few days, so hope my tea stays cold, otherwise we're going to end sooner. But yeah, hope I can do 80 minutes. Okay, so topic of the day is limitations of graph neural networks. We have been using them for more than a month. Many of you are using them in projects, but I also want to show some of the downsides and cases where they don't perform as well as you would expect. All right? So first we go through a very quick recap. What are graph neural networks and how do we use them? Main idea is we start from any sort of graph. This could be a real network, a synthetic one, could be biodata, could be a social network, and so forth. And then the key idea is that we apply convolutions, and then we produce representations for nodes, first of all. And then later on, we can also try to use these node embeddings as a way to represent subgraph, small structures of a graph, or even full graphs. Okay? So we have this very powerful pipeline with a lot of layers and nonlinearity that allows us to produce these very rich representations of our graph. How did we do this? So some of the key ideas is that we generate our node embeddings based on the local network neighborhoods. Okay? So say A is our target node, and ideally the kind of information that A has is not only its node features, but also the features of the nodes that are nearby it. Okay? So the idea is that we move from this graph representation to something that we call the computation graph. So we say, okay, what are the neighbors of A, B, C, and D? And then these three neighbors will pass messages over A. So they will pass their features, their information, their topological structure. And same we are going to be doing for B, C, and D. So we take these nodes and we aggregate over their neighbors, and we pass these messages all the way through. Okay? So the key idea is now, thanks to this aggregation, thanks to this information that we aggregate, we pass it through a set of neural networks. Okay? So now this is going to be our notation. We're going to be having these gray boxes, and here basically you can expect some magic happening. So basically some nonlinearity brought in by the neural networks, and we're going to be producing a representation for our node A. Okay? So that's how we produce our node embeddings. Now the topic of today is what's inside these boxes, and can we do these boxes? Can we have them more discriminative, more powerful? So we have seen a few examples last month, right? So there are many different GNN models. We cover briefly the standard graph neural network model. We talk about graph convolutional networks. We talk about GraphSAGE. We went through very quickly through the graph attention networks as well. If you see from this very short list of papers, there are many more architectures out there. If you get passionate about this topic, you can read 4 months, and it's a relatively new field, okay? But there is a lot of activity going on. So plenty of different architectures. Each one of them basically plays on replacing the content of this box, running different kind of aggregations, and so forth. So let me remind you the few architectures that we covered during the last lectures. So one of them, like the key one that we talked about, were graph convolutional networks, published just a couple of years ago. And I will just highlight the key characteristics that we're going to be using today throughout the whole lecture. So the idea there is we said, okay, once we have the representation of each node, we're going to be applying mean pooling. And I'm going to be refreshing you this idea of pooling, but if you remember is basically we take the vector representation of each node, and then we're going to be taking the mean among the different components. And then in this case, we do a linear combination plus an activation layer that brings some nonlinearity. So that's how we basically design our graph convolutional networks. We have also seen GraphSAGE, pretty much the same concept. We are going to be still aggregating over neighbors, passing the data through a neural network. In this case, what we do is first we use a multi-layer perceptron to produce the representation of a node, and then we apply max pooling among all these representations. Again, refresher about max pooling, we're taking the max component of each vector node. So now we recall how they work on a very high level, and as I was mentioning before, we define one computation graph per node, okay? So the key idea is, so we're gonna be using this example graph for a while, and each one of these, of the node in this graph will elicit a different computation graph, okay? So if you have some time to spend, you can go through each single node and you will see that each one of them is the expansion of the two-hop neighbor of each node in our graph, okay? So as you can see, each one of them looks slightly different. And the intuition that we want today is we want our graph neural network to be able, even just from the topological features of our computation graph, to understand that our yellow node is different from all the other colors. Okay? So first I will show you some counterexample when this doesn't happen, if the shape of the computation graph is exactly the same, and then later on we're going to be seeing a network, a GNN that allows us to distinguish also those cases. All right. So this was the first idea that we're building on, so the fact that we know now how to build a computation graph. Then we said, once we have the computation graph, we can obtain the node representation by neighbor aggregation, and we talk about the different ways in which we do it. So we have seen in GCNs we use different kind of poolings, different ways of building the node representation, but at the end of the day, the concept is always the same, okay? So we have a step where we produce a representation of a node, a step where we aggregate over the neighbors until we obtain the final representation for our node. And one last idea that I want to refresh that is going to be also useful during today's lecture is the fact that we can bring this pooling to the next step and not only do it at the level of producing the node representations, so we don't only use it to aggregate over the neighbors, but we can take all the different node representations of the node belonging in our graph and then pool them. And we can pool with different strategies. It can be a sum pooling, a mean pooling, and so forth. And then we obtain one final representation for our graph, okay? And this is extremely useful in case, for instance, we want to do graph classification. So the idea is like we have a large collection of graphs, and we want to come up with one representation, one fingerprint for that graph, and figure out if there are other graphs matching it or not, okay? So this is the full, let's say, the different level of granularity with which we can work thanks to these representations. Now, the good news is, and the reason why we are talking so much about GNNs in this course is because in the last few years, they kind of, stole all the attention from most of the other techniques and they achieved state-of-the-art in all the most important tasks that you can perform on graphs. So they have state-of-the-art in node classification, in graph classification, in limb prediction, and so forth. So that's the reason why most of the times you came to my office hours and you asked me what can I do in my project with this data set. I ended up recommending you one of those techniques just because they are so powerful today. But are they perfect? So the fact that something is powerful, achieves state-of-the-art, should never in some way trick you that it's a silver bullet that solves every possible problem on that kind of data structure, all right? So that's why we wanted to introduce this lecture at the end of the course to tell you there are also some limitations to GNNs. They don't work in all the possible real-world data set that you could be using. Rather, the state-of-the-art results that I just showed you before, they've been obtained on very famous and common data sets, but there are some corner cases where GNNs will underperform. So which are these corner cases and how can we solve them? So we're going to be talking about two main limitations today, okay? The first one is the one I've been alluding to for a while. So the fact that some simple graph structure cannot be distinguished by conventional graph neural networks, okay? So let's think about this very simple case, and we're gonna go in depth, dissect it, and explain exactly why this is happening. But these two small graphs, both of them with 4 nodes, but just a different adjacency matrix. If their input features are uniform, okay, so in this case you see all our nodes are yellow, so all our node features are the same. This is the notation that we're going to be using today. Then can a GNN distinguish between these two small graphs? And the answer is, at least for GCN and GraphSAGE, they will fail to distinguish the two of them, okay? And we're going to be seeing why this can be a problem, especially for downstream tasks, let's say when we try to do graph classification. Another problem which you might have heard of quite for sure in general in deep learning are adversarial attacks. And it turns out that they don't only apply to images, other domains, but they also happening with graphs. So GNNs in general are not robust to noise in graph data, right? And we're going to be seeing a relatively easy but elegant technique that allows us to, with very few node features perturbation or edge addition and deletion, allows us basically to flip the classifications of our nodes, okay? So these are the two main classes of limitations that we're gonna be covering today. So here is the outline. First, we're gonna be going through the limitation of conventional GNNs in capturing the graph structure. Then, second part, we're gonna be talking about vulnerability of GNNs to noise in graph data. And then if we have a bit of time left, I'm gonna be, showing you some open questions and future direction that our group and other groups working in on GNNs in the world are currently doing research on. All right? Any questions up to now, or shall we go forward? Was a question there? Okay, let's go. So first part, limitations of conventional GNNs. So as we were saying before, given these two different kind of graphs, can a GNN map them into different graph representations, okay? And obviously this is a very important condition for a classification scenario. If you think about it, this could be just standalone graphs, they could be subgraphs. In general, like if this kind of small structure is not distinguishable in a GNN, clearly there is a limitation that we would like to avoid, right? And essentially, the problem that we're trying to solve here is the one called graph isomorphism test, which has been studied in graph theory for decades. And the bad news is that there is no polynomial algorithms that exist to distinguish every possible graph in the general case. There are a lot of heuristics, and we're going to be seeing also a test which is very powerful and still runs in real time. But the expectation is that if the graph isomorphism test is so expensive, then we shouldn't expect GNNs to perfectly distinguish any possible graphs, right? Because as we have seen, they're pretty much linear in terms of computation. So we have to carefully design a GNN in terms of to be able to distinguish each possible different graph structure. So how are we gonna do that? And how well in the end can GNNs perform the graph isomorphism test? So we're gonna basically be running this parallel today throughout the whole lecture, at least for the first part of the lecture. We're gonna be trying to have a GNN which performs as close as possible to the graph isomorphism test, okay? And as I said, this will require rethinking a bit the mechanism in which the GNN captures the graph structure, okay? So contrary to what we've seen in GCNs or in GraphSAGE, we're gonna be changing, some strategies in the aggregation to make sure that we can also capture just the difference in the topology of a graph. So let's go through the example as I promised before. We're gonna dissect it and go step by step, okay? So graph on the left, as you can imagine, each computation graph for our nodes, as you can see here, we look exactly the same, right? So remember we said these are yellow nodes that have exactly the same node features, and the topology for each node and the neighborhood of each node looks exactly the same. So basically, node 1, 2, 3, and 4 will have exactly the same computation graph. There is no way for a GNN to understand that these nodes are different. Conversely, if we go on the right and we talk about our green graph, then our nodes 1 prime, 2 prime, 3 prime, and 4 prime will have slight differences. So even if the node features are exactly the same, then the shape of our computation graph will be different, okay? So how can we leverage the fact that the topology of the computational graph will be different? How can we use this to distinguish that these two graphs then are different? So we're gonna be calling our computation graph, basically these are rooted subtree structures. So we root them on our target node, and then we build a subtree of arbitrary depth. Usually we work with two-hop neighborhoods. Reason is most of the common GNNs that we've covered in the course do that. We have also seen, for example, at the very beginning of the course, real-world networks have very small diameter. So we cannot really afford to work with like a 4 or 5 hops, because that will mean pretty much traversing the whole graph every time, okay? So that usually the 2 hops is a reasonable trade-off to work and build our computational graphs. Now, our expectation is if we have already the most possible discriminative GNN available, then our GNN will map different subtrees into different node representations, all right? So this is our ideal scenario, okay? Like for 1, 2, 3, and 4, the representation will be the same, so our coloring will be the same, while for 1 prime, 2 prime, 3 prime, and 4 prime, the representations will be different, so 1 and 4 are different. You can see it very clearly at the bottom, while 2' and 3' are the same as expected, because of course there are two nodes in that graph that are absolutely symmetric in terms of topology. So at the end of the day, what we really want is a way to build an injective function that goes from our node to its representation. Now, in case you forgot your first year of maths, I'm going to give a very quick refresher what it means for a function to be injective. So basically, a function is injective if it maps different elements into different outputs, okay? So as we see here, we go from domain A to B, and there are some elements here that map to the same output, while in the case of the injective function, each element maps to a different output, okay? And it's very intuitive why we want this property to hold, correct? If we have multiple nodes that all map to the same output representation, then we will not have enough discriminative power for the GNN to understand if nodes are different or not, okay? All right, so now we said we want to make sure that our aggregation is injective, and one nice property that we can leverage to make our life much easier is the fact that the entire neighbor aggregation is going to be injective. Every step of our neighbor aggregation is going to be injective, right? So we don't have, in some sense, to guarantee that our full pipeline is injective. It's enough that each single step is, all right? And this is important because, again, in this case, we're just working with a 2-hop example. Say, we had even more hops, it will become even much harder. In this case, we just have to care that each single step is an injective function, all right? Everything clear up to now? All right, I'm going to fix my voice. All right. So what is neighbor aggregation? Let's try to think about it in a different way. Until now, we always thought about it as pretty much a way to traverse a subgraph. Now we want to think about neighbor aggregation as a function, all right? So neighbor aggregation is essentially a function over a multiset. So why do we want to work with multisets? For two reasons. So of course, they will be set with repeating elements. That's why the multi in the set, because there will be nodes that have exactly the same features when we do the aggregation. So we wanna make sure that we can retain those nodes if they occur multiple times. And at the same time, we don't care about the ordering. As we have always talked during the course, we want operators that are invariant in terms of ordering. The reason is it's also extremely hard to define a meaningful ordering on a graph. Right? So we want all our operators to be order invariant. So now that we explained this, we can see this mapping. On the left, we have our neighbor aggregation that we've been seeing when we think about it in terms of graph, and this should be equivalent basically in once we have taken all the neighbors together, we apply a function to all of them, and we obtain some sort of representation. Okay. So this will be our multiset from that set of neighbors. These are just some additional examples of multiset that you can think about. So in this case, you will have two neighbors and they have different features. Or in this case, that's why we care about a multiset, because there are 3 neighbors in total. 2 of them have the same features, 1 have a different feature set. So once again, every time the color is the same, it denotes that we have the same set of features. Okay. So that's why we work with multisets. Now, why it's important to frame the problem in this way. Basically, the discriminative power of a GNN can be characterized by that of a multiset function. So rather than thinking in terms of how a GNN behaves, now we're going to be thinking about how a multiset function behaves, how can we define them, and then if we are sure that we can bring in the injectiveness and the discriminative power that we need, then we know that we're going to be solving our problems on the target GNN. And we're going to be doing, once again, our analysis first on GCN and GraphSAGE, because I've seen them during the course. So I'm going to be showing you that they have shortcomings, and now I'm going to be proposing you a new model that overcomes this issue. All right? So first case study, GCNs. So as I said at the beginning, the way in which a GCN performs the aggregation is the following. So there is a linear combination, there is an activation function, and then it performs mean pooling among the features. So just as a reminder, this is the idea of how max pooling and mean pooling behave. So max pooling, you see, we take the max component, per each area of that matrix, per each submatrix. So you have 20, 30, 112, 37, and then average pooling instead is we take all the components and then we produce the average over them, okay? So reminder what the GCN does, it's using the average pooling part, all right? So that's how the way in which it's gonna behave. So can you think of a case where by changing the neighborhood, we're gonna be getting exactly the same kind of representation? Like how can we fool a GCN in believing that two neighbors are exactly the same, even if their cardinality is different? Think about it for a second. Like how can you fool an average?
If you lower something within that neighborhood by the same amount that you raise another thing. So if you take one node and increase its value for some feature that you care about, but then take its, all of its neighbors and decrease it by its.
Oh, cool. Okay, yeah, so one way you could do it actually is through, you could have some features changing in one node and then you can lower them uniformly in the others. There is also an even easier solution compared to that.
You need only to make this like the average to be the same.
Correct.
So you can just decrease the number of neighbors and adjust the sum such that the average remains the same as with different number of neighbors.
Perfect. By not changing anything, this solution is the following, right? So you keep the proportion exactly equivalent to the previous multiset, and you can keep on adding copies of the same nodes, all right? So that's the easiest way in which you can fool a GCN. So we had one yellow node, one blue node, and now we have two yellow nodes, two blue nodes, and of course now this is not injective, right? Because we have two different multisets, but both of them, thanks to the mean pooling, will be mapping exactly to the same output value, all right? So now we've seen why a GCN will fail in this case. Let's go to the next case study. So let's talk about GraphSAGE. As you recall, we said it produces the node representations with a multi-layer perceptron, and then it applies max pooling over these representations. Again, that's what max pooling is. As a refresher, how do we fool this? Yeah, it gets even slightly worse if you think about it. So given that it's not mean, it's max, it's enough that you can even add the same distinct elements multiple times. You don't even have to preserve the proportionality anymore, okay? Because it will take the max of each component, right? So if the blue node appears once, appears 10 times, doesn't make any difference. So it's not injective also in this case. Okay? All right, so I guess I convinced you that there are some limitations in GNNs and GCNs and in GraphSAGE. How do we fix this, okay? How do we overcome this problem, all right? So let's start from a theorem which we are not gonna be proving, but I'm gonna be pointing you to the paper that covers that. So it's very intuitive why, so that's why we talk about it. Basically, you can think that any injective multiset function can be expressed in this form. So there will be some nonlinear function phi at the beginning, and then we basically sum over all the possible multisets, and there we apply a nonlinear function to each multiset. So as you can see here in the bottom, S is our input multiset. We have one yellow node, two blue nodes, and what we do is we apply a function for each node. We take their summation, and then we apply another nonlinear function to all of them together. So that's the way in which we can model any possible injective function on a multiset. Now, the interesting thing is that, as you might have seen in other courses where you talk about neural nets, the starting courses on neural nets, a multilayer perceptron is a universal approximator of functions. So if and we have seen that in GraphSAGE, for example, we use MLPs to produce node representations. Then we can, of course, use MLP in our new GNN design. And this MLP will allow us to approximate any possible function. So we can basically use a set of MLPs to come up with an injective function over a multiset, okay? So this step is very important because we want to build a graph neural network. So we want to have neural networks to to model our functions so that we can train them over our data. Therefore, we needed a way to be able to find the right MLPs through our training process, rather than just hard coding a set of injective functions. Okay. So, what the outcome of this reflection is the fact that we propose a new model which is called Graph Isomorphism Network, or in short, we're going to be calling it GEAN. It has been published a few months ago. It's coming from our group, and the key difference is, apart from the MLP, which we already discussed about why we need to use it to model our injective function, rather than using mean or max pooling, we're going to be using sum pooling. And the idea there is that the fact that we're going to be using sum pooling allows us to distinguish between these two different cases. Okay, so this was the case where also GraphSAGE was failing. If you think about it, now we have different representations for each node, and the fact that now there are two blue nodes will change the output of the sum pooling, because there will be an additional component coming from this additional node. Therefore, intuitively, these two aggregations will map to different values. Okay? And in this way, we built our injective neighbor aggregation, and we expect our new GNN architecture to have more discriminative power compared to the ones that we discussed beforehand. Okay? All clear? Sounds good? Okay, perfect. So, how do we actually use this now? Like, how do we leverage it? Oops. All right. So this is the idea. We're back to the graphs that we were seeing before. So we have our red graph where each node is mapping to the same color, and then we have our green graph where we have three different colors. Basically, two nodes are the same, and then we have blue and green, which are distinguished. And our expectation is that basically the sum pooling will also give us injective graph pooling, all right? Because we can now sum all the representations of these different nodes. So if we do sum pooling over these different nodes for the second graph, then we're going to be getting different graph representations. So the expectations is that GEAN will perform better on the graph classification task compared to what we've seen with GCNs or GraphSAGE, okay? So what we've seen is that GEAN allows us to achieve maximal discriminative power by using this injective neighbor aggregation, but how powerful is this? Okay, so I'm going to be showing you some experiment, and also I'm going to be showing you a mapping to a graph isomorphism test to convince you that this is much more powerful than what we were talking about before. So the way in which GEAN has been, conceived and thought about is it's very closely related to the Westphal-Lehman graph isomorphism test, which we're going to be calling the WL test from now on. Okay, so this test is more than 50 years old today. It's extremely well known and used by everyone who works with graphs. The reason is its complexity is in the order of the number of edges, so it's a relatively cheap and efficient test to run on graphs, and it's extremely capable, and it distinguishes most of the real-world graphs. Okay, so that's why it has been adopted and used for so long. Now, what we want to do is we want to show that GEANs are as discriminative as the WL test. Okay, and how do we do that? So basically, we try to show that the WL test and GEAN work as exactly the same kind of functionality. They have been built with the same kind of design. So what does the WL test do? First of all, it maps different rooted subtrees to different colors. And this is the same thing that we've seen to the injective neighbor aggregation in GEAN. So basically, the WL test goes one level at a time. So you can think of the WL at level 0, and what it does is it counts the number of nodes in a graph. Okay, so we'll tell you, okay, this graph has 4 nodes, and this graph has 4 nodes as well. They all have the same colors, so we'll try to recursively go one level deeper. Okay. Then what it will do, if you run the WL test at level 1, you will find out that each node here has 2 neighbors. Okay, but then here some nodes have 3 neighbors, some nodes has one node has just 1 neighbor. So do you think that we need to go all the way down to 2 levels with WL test or not? like how much information do we need to distinguish that these two graphs are the same or not? We don't need to go all the way down to the second level, right? So think about it in this way. You don't have any graphical representation of this graph. You have, someone gives you two different data sets and they tell you these are graphs. Load them in Snap or any library that you like and get stats and tell me if they're the same graph or not. The very first thing you will be doing is you count the number of nodes, okay? And if they're not the same, of course these two graphs are not the same, right? Then number of nodes coincides. Then the second thing you can try is you can see the node degree distribution, okay? And that's what we do at level 1. And what we're going to be seeing here is that, okay, our graph on the right has a different node degree distribution compared to the graph to the left. Therefore, these two graphs are different. Okay? So that's pretty much what the WL test does. And at each additional level, we bring in more information. There clearly becomes more expensive, right? The more we expand the subrouted tree for each node, the more it becomes expensive because we have longer traversals. So that's why it's conceived in this way. It goes one step at a time until the node coloring remains stable. Therefore, it knows that it found a unique representation, and then it will be able to tell if these two graphs are the same or not. Okay? Sounds all clear? Awesome. All right. So now we got a grasp of how the WL test works. So this is exactly what I was telling to you before. Now what it performs is pooling. Yeah, I'll go. Question.
You said we keep going steps until we sort of stabilize on the color of the node. For trivial graphs like this, that makes sense. For very large graphs, is there a similar process or is it the same process? Because surely there'd be almost unique nodes.
Yeah, so for very large graphs, the expectations is that you will find differences very early. If that's not the case, then it's basically up to you how much you are willing to wait and how much computation you're willing to spend on that. But ideally, like once you have, as I was mentioning before, if you start to generate more than the 3 open neighbors per each single node, unless you have a toy graph, you're not going to be able to afford to run something of that magnitude. Yeah. So most of the times you find an idea very quickly. Now, it's also interesting to talk about the fact that most of the graph isomorphism tests happen on smaller graphs compared to what we discussed at the very beginning of the course. Like in general, no one will go and check if there is isomorphism between the Twitter graph and the Facebook graph, or the web graph and the Facebook graph. Usually this test is not applied to gigantic graphs. It's more applied to molecules or small biological networks and so forth. So in the domain of a few thousands of nodes. Make sense? Thanks. Great question. Okay, so back to this. Basically, what I was saying is the way in which now the WF test works is it performs graph pooling as we have seen in GNNs in general. So what it does is it's counting how many nodes of a certain color we have. Okay, so he will say, okay, our graph on the left has 4 reds. Our graph on the right has 1 blue, 1 green, and 2 purples. Therefore, these two graphs are different. Okay, so as you've seen, basically, Gene is approximating the way in which the WF test works, apart from replacing these boxes with neural networks, with MLPs. Okay? Perfect. All right, so now we have an understanding of how the WF test works, the fact that they are basically operationally equivalent. So our expectation is that the WF test then can distinguish the same graphs that Gene can also distinguish. All right? Now, how does this impact the real-world performance, and are there some still limitations that we can find in Gene? And of course, that's the case. As we said before, this is still not perfect. It's not going to be able to distinguish any possible graph, but it's a very good trade-off. So, for example, in this slide here, you can see some corner cases where also the WF test fails. And these are pathological examples, basically, which have been built with the sole purpose of fooling the WF test, okay? So a G-skip graph, in this case, the notation is the following. 11 tells you the number of nodes in our graph, and the second argument is how many nodes you have to skip to connect, to have this skip connection in this chain graph, basically, okay? So you build this circle, each node is connected to its neighbor, and then you also have a skip connection that goes 2 nodes away, or in this case, 3 nodes away, and so forth. So If you like, you can build, you can try to draw your own computation graph rooted on each node of these gskip graphs, and you will see that they're all going to be looking exactly the same. Okay, so each one of these nodes has 4 neighbors, and every time you expand, each of those nodes will have 4 neighbors as well. So the WL test will fail on that corner case. Of course, most of the even small graphs that we care about don't look in this way. Like even molecules are not built on purpose to fool the WL test. Therefore, it's not something that we are too worried about. But if you're interested, there is also a very recent work done which tries to basically expand the way in which gene works also to these corner cases. But the key catch there is that now the time complexity will become exponential again, okay? Which is something that we can rarely afford when we're working with such large amounts of data, okay? Cool, so let's go to some experimental results just to convince you how well this is working. So all the results I'm going to be showing you about gene are about graph classification. Some of the data sets that have been used are social networks or biochemical graphs and so forth. On this plot, we see the training accuracy of different GNN architectures. In this case, we are working on a proteins data set. And the curves are the following. So the one that we care about right now is this orange and red, which is gene. Then we have GraphSAGE and GCN pretty much performing similarly. So there is a quite substantial gap, like a 0.2 in terms of accuracy. And this line that you see at the top, we're not going to be explaining exactly what are WL kernels. But basically, the idea is that if you apply the WL test on this data set, it will allow you to perfectly classify all the proteins contained in that data set, okay? So it basically tells you that gene is as powerful as the WL test when applied on this kind of data set. So it can reach pretty much 100% accuracy there, all right? So this is about the proteins data set. Now we run this also on different kind of data sets. So I think this is a chemical data set. These are movies. This is a social network on Reddit. So again, gene is always very close to almost a perfect graph classification. And now we're going to be analyzing, in case you notice, this line at 0.5, so 50% accuracy. This is a binary task, which means basically, in this case, the GraphSAGE was a completely random classifier. So why do you think this is happening? And I gave you a clue here. I said Reddit dataset does not have node features. So what do you think is going on, based on everything that we talked about in the last half an hour or so? This is on test data. I forgot to mention that. So this is the accuracy on the test data set. Yeah.
Since all the nodes are exactly the same, uniform, then all the things we're talking about were like different node numbers being the whole impact.
Correct.
That's happening throughout all of this GCN and GraphSAGE. So we're basically in like the worst case scenarios of those.
Correct. Perfect. So the answer is there are no node features, so we have no way to distinguish the nodes apart from the topology. And every time we do the neighbor aggregation for nodes in our Reddit dataset, we find enough neighbors to sample. Therefore, all the computation graph rooted on each node of our Reddit dataset will look exactly the same. Therefore, there is no way for a GNN, for a GCN, or for GraphSAGE to understand if these graphs are different or not, all right? And instead, in this case, gene shines with more than 90% accuracy. And it also performs better even on datasets that do have features on the nodes. It still does relatively better on those tasks as well. Okay? Perfect. All right, so in some sense, basically, one way in which you can read this table is the following, is the fact that, of course, node features do play an important role when it comes to perform node classification, but there is an edge that you can bring in by also being able to leverage the graph structure. And this gap that you see between, for instance, a GCN and gene is the gap coming from the fact that we're also learning from the graph structure and not only from the node features. All right? Perfect. So let's recap the first part, which is we have seen that existing GNNs use non-injective neighbor aggregation, therefore have low discriminative power. Then we talk about GN, which instead uses injective neighbor aggregation and is as discriminative as the WL graph isomorphism test. And GN achieves state-of-the-art test performance in graph classification, as we have just seen on this last slide. Cool. If there are no questions, we jump to the second part. Let's go with that. So now we're going to be talking about vulnerability of GNNs to noise in graph data, or in some sense, adversarial attacks on GNNs. So I'm quite sure you have seen this example multiple times. I think it went on the media as well, possibly not with the pandas, but with other animals. But the key insight here is that deep neural networks are vulnerable to adversarial attacks. And I'm quite sure this case comes from ImageNet. The idea is that attacks can be implemented in the following way. We can add a layer of noise which is imperceptible to the human, but we'll be able to completely fool the classifier. Okay, so we go from this image, which is classified as panda with almost 60% confidence. We add a very small layer of noise, which drives the gradient towards the direction that we care about, so that we produce a misclassification. And then it returns not only the wrong label, gibbon, but also it can boost the confidence of that prediction up to 99%. And apart from the low resolution of this image, a lot of examples that you can see, you will basically find out that it's very hard for humans to distinguish that there is a layer of noise applied on top of this panda right here. Now, this is not as scary as when these kind of attacks are applied to stop signs, if you're in a self-driving car or so forth. So this is interesting per se as an academic example, but you can imagine it can have a great impact in the real world as well, right? Because you can start to fool your vision systems. So what I'm going to be showing to you today is the fact that these attacks do not only apply to the domain of vision, but unfortunately they can also be applied to graphs. And adversarial attacks are very common in application of graph neural networks, because if you think about it, graphs are used in very how to say, in domains where there is a lot of money involved and revenues involved, okay? So for instance, search engines, recommender systems, social networks, and so forth, okay? So the idea that, for example, we talked about it at the beginning of the course, that you can think of the web graph as a giant graph structure where if you know exactly how to change the pages and the links among the different pages, then you can change the credibility and the importance of specific websites compared to others. And actually, there are also some professions based on optimizing results on search engines. So you can think that if there is a way to exploit this kind of vulnerabilities, there will be, of course, people and companies interested in exploiting those exposed vulnerabilities, okay? So that's why this is very important, possibly as much as the example we've seen before. Question?
I have an intuitive understanding of what an adversarial example is for, say, an image classifier, but I don't have an intuitive understanding for what an adversary is in a social network, for example.
Okay. Let me try to give an example. So for instance, in social networks, you always see friend recommendations, right? So you're on Facebook or on Twitter, and they will recommend you to follow certain people. Now, if you are someone who's very much interested in spreading fake news, which is the hottest topic of the past few years, then what you would like to achieve is to make sure that your fake account or your bot account is continuously recommended to a lot of people, so that you will get a lot of followers very fast. That's exactly one use case that is very dangerous, where you want to avoid potential attacks, okay? So that first example that came to my mind, but I think it's pretty powerful. Question?
So in terms of the actual action you would use to make yourself recommended, would that just entail creating lots of fake accounts or having fake interactions with other fake accounts?
Great question. So I will paraphrase your question, which is, how much do we have to tamper with the real graph in order to be recommended all the time? What I'm going to be showing you today is that it's much less than you would expect. You don't have to have control over 1/3 of the network. You need to have control over a few nodes and edges. In case you have studied distributed systems, you might have heard about Byzantine attacks and this idea that you need to take control over 1/3 of the nodes to change the outcome of your distributed system. This is not the case. It's much worse in some sense because you need very few targeted attacks to change the outcome. Okay? Great question. Thanks. Okay, let's go. So now I'm going to convince you if GNNs are robust to adversarial attacks. I think I spoiled you the story, so the answer, of course, is not. But luckily, there are people working on that. Some of them are in this room right now. So there is definitely work going on in making GCN more robust. So let me give you a recap of things that we talked about already in the course. We've been talking about semi-supervised node classification since the first month, where I gave you the lecture on node classification even before we covered GNNs. And the scenario that we have here is we have our initial graph, which is only partially labeled. Okay, so only a few of our nodes will have a label, and we want to infer the labels for all the other unlabeled nodes. Okay, so this is the what we want our GCN to produce for us, a set of labels that were remaining in the graph. So the way in which we did that is the following. So a bit of refresher on the notation. So we have our adjacency matrix A. We have a vector. We have a matrix with all the node attributes, and then we have our A hat, which is just the renormalized adjacency matrix. And what we are doing is a simple two-step GCN message passing. So this is the first step. You remember, it's just a linear combination. So we take the renormalized adjacency matrix, we take all the node attributes, and then this is the weight matrix that we're learning. So this is our first step, and this is our second step of aggregation. And then we take a softmax, basically, to obtain a probability distribution of each label for all our nodes. We do the training, minimizing the cross-entropy loss on the label data, and then in testing, what we do is we apply our model to predict all the missing label in our graph. Okay, so this is how we perform semi-supervised classification with a GCN on our graph. So now that we clarified what is the context, how can this be attacked, and how easy is this to attack, and what are the kind of attacks that we can perform on this scenario? So there are different attack possibilities, and let's first of all distinguish the different domains. So we have both the target node and we have the attacker node. So the target node in some sense, let's say, is our fake news account on Twitter that we want to boost and we want to recommend to everyone. Okay, and the attacker nodes instead are some of our side, fake accounts or bots that we can manipulate in order to boost as much as possible the results. So our target node T is the node whose classification label we want to change. Let's say our label is to be recommended, yes or no. And then the attacker nodes are the nodes that we can directly modify. So like in this case, for example, some of the direct attacks that we can do, for instance, we can modify the target's feature. So say our fake news account is about to be banned, then we can try to change the content that we post. We can try to sort of to avoid the Twitter spam filters. We can also add connections to the target. This is very common in social media where we can buy likes or followers. So we can get from these spam farms and we can get many more followers to our bot account, or we can also remove connections from the target. So we can cut some edges in case our fake account is followed by a lot of unfollowed and untrusted users. Then we can decide to get rid of them because perhaps Twitter knows that we're being followed from a lot of fake accounts. Therefore, we want to get rid of them. So these are the kind of direct attacks that we can do directly on the target. And the indirect one instead are coming from our attacker nodes. So for example, we can try to change the attacker's features by, we eject the friends of the target, or, we actually follow our target node and then we change our own features. And similarly, we can add connections to the attacker by creating a link or a spam farm, okay? So these are basically the different knob that we can tune, okay? So we can add and remove edges, we can change features, and if you think about it, This is very similar to the example I gave at the end of the node classification lecture, where we talk about how you can generate a set of trusted users, untrusted users, and then we had this like population of proxy users that try to fool the system in order to let the malicious users not be detected. This is pretty much the same scenario here, where our attacker nodes can basically decide if they want to expose malicious features or not, and if they want to be connected to our target node or not, and so forth. Okay. So now that we have all these different tunable, how can we turn this into a mathematical model, and how can we show how powerful these attack possibilities are? So let's start from the very high level idea, which is similar to the question that I received at the beginning. So what we want to do is we want to maximize the change of the predicted labels of target nodes. So we want to make sure that, say this is the class 2 is not recommended and class 3 is recommended. We want to bring down this probability, and we want to bring up the class 3 probability. But this maximization has to be subject to a limited amount of noise in the graph. So we don't want to act on the whole graph, change all the features and all the connectivity. Rather, we want to do just a few modifications. So like in this case, we change 2 feature values, we cut one edge, and we added one edge, and this already leads to this kind of misclassification, all right? So this is the very high-level goal that we have in mind. Now, let's turn this into formulas, into a model, and let's see how we can make it work, okay? So at the end of the day, what we want to do is we want to find a modified graph that maximizes the change of our predicted labels, and our objective function is the following. So we're going to be producing, first of all, a modified adjacency matrix. So we said we want to be changing some edges in our graph. We also want to modify some of the node features. So we want to basically then maximize the outcome of our predictions. So we don't want our new classification to be the same as the old. And this means the following, basically. So we want to increase the likelihood that the target node B is going to be predicted as C. Okay, so this term, basically this probability goes up. And then at the same time, we want to decrease the likelihood that the target node B will be predicted as the old label that we don't want to see anymore. Okay, so this part of the formula tells us basically that. And now at the same time, we want to make sure that we are going to be retraining the GCN on the new connectivity, right? Because we said that we are changing our adjacency matrix. So every time, recall, this is our semi-supervised node classification with a GCN that we have seen before. So what's happening here is that every time we're changing our matrix, we're also retraining the whole model. And if you think about it, this is possibly one of the main shortcomings of this approach in some sense. The fact that it's going to be expensive to optimize this objective, because at each change of connectivity, we have to train a brand new GCN, okay? And at the bottom, basically, this is encoding what we said at the beginning. We want to make this happen with the least possible amount of modifications. So we want to have our node features and our adjacency matrix, the new ones, to be as close as possible to the original ones, okay? Now, as I mentioned, in practice, we cannot exactly solve this optimization problem because graph modification is discrete. So we don't remove only partially an edge, right? So we don't have a smooth optimization surface where we can move with a gradient function. Here, the only actions that we can do are either changing the node features or adding or removing edges. Okay, so this inner loop that we've seen here involves a expensive retraining of a GCN. So to make this question, yeah, sorry.
Adding training each time the GCN, shouldn't it be fixed for A and X? Because that Adversarial example is such that.
Sorry, can you repeat it?
By retraining the model with changed adjacency metrics and node features, like the goal of an adversarial example is if it is that even if it is trained in a same network, you change some of your features such that the model a trained model is not able to classify you correctly, right?
Yeah, so let me understand. Let me see if I understood the question. You're asking if we change the training model, why do we need to retrain it again? Okay.
Shouldn't we like have this expression over theta, which is trained over a and x?
No, the idea is like we're changing the adjacency matrix of the graph, right? So the only way to find out if on that graph the classifications will be different is to retrain the GCN with the new adjacency matrix. So we want to see if by removing an edge and adding another edge, the classification of that specific node will be the same as before or will be a different one. Okay? So there is no, like the only shortcut that we can take here is instead of trying at each single step to retrain, we can try to come up with a new configuration of the adjacency matrix and a new set of features and then say, okay, we have reasons to believe that this will give us a misclassification and then we retrain all in that case. Okay, so as one of the ideas here is what we want to do is we want to try to obtain an approximate solution rather than an exact one. So for example, we can try to either greedily choosing the step-by-step graph modification. So like we have a set of modifications and then we retrain. Or another idea would be to remove the nonlinearity in the GCN. So we remove the ReLU activation. And then in that case, we can work in closed form. So we don't have any more to do the training. We just expand the formulas. Or some other details you will find directly in the paper that I linked at the beginning, okay? But yeah, there are some trickery here and there to solve before making this work both fast and correctly. Okay, so let's go through just a few examples so that I convince you how this is working. So back to we are in our semi-supervised node classification setting, and in this plot what you can see are the class predictions for a single node, but they're produced on 5 different GCNs with slightly different random initializations. So on the y-axis, you see the predicted probability, and then on the x-axis are the labeled probabilities for each class. Sorry, the probabilities for each class. So from all these runs, you will see that our target node has classification with class 6, which is the one that we consider correct, and in all the cases the probability is very high, okay? Now, what we care about is the classification margin, which is the difference between the highest probability and then the second highest probability that we see in our plot. So in case this margin is very small, then we have high uncertainty of the classification that we generated. Conversely, if it's very high, then we trust this classification. So not only we care about the fact that the highest probability is assigned to the class that we want to, that we want to fool the classifier with, but also we want to have a high margin so that the attack is very reliable. And if anything, no one can use the confidence of that prediction as a signal if an attack is happening or not. So that's how it looks like by simply easily manipulating only, basically applying only 5 modifications to the graph structure. This is exactly how it's going to look like. So we can switch from class 6 to class 7. As you can see, our margin is even much bigger than before. And interesting is also to notice the fact that this is not a small graph by far. So you could think like, okay, these are 4 modifications on a graph that has 50 nodes like a molecule. It's a graph with more than 2,000 nodes and 5,000 edges, okay? So this is to remind you what we were mentioning at the beginning of this part where we said how much do you need to interfere with the graph structure in order to obtain a successful attack. And as it shows from the results, is very small amount of modifications, okay? So that's why this technique is very powerful. So I hope I convinced you that GNNs are not robust to adversarial attacks now. Question?
How much does a successful attack of such small scale rely on sort of complete information of the classifier and of the whole network? Could you do it with only local information of the network?
So if you think about it, great question. So the question is, how much does this rely on the fact that your model has a holistic view over the graph? In reality, it doesn't, because a GCN doesn't have full knowledge of the graph. Like it works by means of computational graphs. And as we have seen, you're always performing a 2-hop aggregations at most. So if anything, this attack is performed with just local knowledge rather than global one. Okay? So if you attack something like a graph kernel or older techniques that we didn't talk about, which actually leverage the features of the whole graph, yeah, your point will be absolutely valid. But in this case, the model is totally oblivious of what's happening 2 hops away. So it's pretty powerful also for that reason, yeah. Of course. Thanks. Okay, I think we have a few minutes left, so we can just go quickly through some open questions and future directions. So one idea is there are a lot of applications going on of GNNs on the science domain. So for example, GNNs are being used to find out if certain molecules are toxic or solvable. So basically, they try to classify different molecule properties and predict them reliably. Or in the case of, for instance, of biological networks, like a very famous one is the protein-protein interaction networks. Then we give as an input the protein structure to a GNN, and we try to predict what's going to be the activity of that specific protein. So these are all new venues where GNNs are being applied with great success. But of course, every time there is a new domain, it also involves new challenges and it raises new problems. So what are some of the challenges of applying GNNs to real-world data? The first one, which in some sense, these problems today, I'm telling you in the context of GNNs, but they are overarching problems in machine learning, right? So the first one is very common, is the scarcity of labeled data. That's one of the reasons why we often talk about the fact that if we had only unsupervised techniques that performed as well as the supervised ones, then we will be dropping the supervised techniques because obtaining labels is extremely expensive. And the problem there is usually we have labels only for small data sets, and our models will then overfit to small training data sets and then will not generalize well to larger ones. Okay? So this is the first problem that we're facing. And one that is very much connected is also the auto distribution prediction. So the idea is that the test examples tend to be very different from what we train on. Therefore, our models typically perform poorly when we try to generalize to real-world data. Okay? So how do we try to overcome with issue in GNNs? The one promising direction that we're working in our group as well is that one called the GNN pre-training. So what we do is we give a lot of, for instance, unlabeled molecules or very well-known chemistry databases as an input to the GNN. So basically, we pre-train the GNN to produce representations for very common data sets in chemistry, and then our GNN pre-trained with chemical knowledge will then be fine-tuned towards downstream tasks. In case, for example, you have taken, I don't know, 2to4n and you have been seeing language models and transformers and so forth, this is something very common nowadays in natural language processing, where we just pass huge data sets to these very deep architectures, and then we fine-tune for specific tasks, such as, I don't know, question answering, for example. So we're trying to do exactly the same for GNNs, large data sets, both labeled and unlabeled, pre-train, bring in as much inductive bias as possible in the GNN, and then fine-tune for additional downstream tasks. And when it comes instead to how to make GNNs more robust, so the open question is how do we defend it against attacks? One problem, one challenge is the one we were mentioning before. It's very difficult to find tractable optimization on this discrete graph data. So the problem that we mentioned before, the fact that we're always retraining GCNs in that inner loop. And at the same time, we also want to achieve a good trade-off between accuracy and robustness. What I mean here is the following. For example, we could avoid doing aggregation over multiple hops or neighbors, and we could just use the node features. Okay, so we could avoid taking into account the edges connecting to the followers, or followers of followers, and so forth. If we do that, of course, we are less exposed to attacks, right? Because we're not taking into account anymore the adjacency matrix. But at the same time, we're also trading off in terms of accuracy because we are not leveraging the structural properties of the graph to make our model more powerful. So these are completely open challenges today in attacks on GCNs. So in case you're interested in doing research on this, you know where to write, contact our lab, and we're happy to take projects on that. And with this, I'm taking questions. This is my last lecture in the course. Thursday, Yuri will be giving the last one on applications of GNNs. This has been great, a lot of fun for me. Contact me if you need any help for projects, and I'm going to be seeing you at the poster session. Thank you.
John Doe.
John Doe,